This is the session on statistical methods for ranking and functional data types. We have two speakers. Our first speaker today is Adam Pintar. Adam earned a Ph.D. in statistics from Iowa State University in 2010 and has been a mathematical statistician with NIST Statistical Engineering Division. His primary focus is providing statistical and machine learning expertise and insight on multidisciplinary research teams. He has collaborated with researchers from very diverse backgrounds, such as social science, engineering, chemistry, and physics. He is a past chair of the Statistics Division of the American Society for Quality, and he currently serves on the editorial board of the journal Transactions on Mathematical Software. He is a member of the American Statistical Association and a member of the American Society for Quality. Please welcome Adam Pintar.
Hello, everyone. Thank you. Welcome to the last session of last technical session of the conference before the keynote. I'm going to talk a little bit about only one of those interdisciplinary projects associated with social science today. This was my first foray into ranking data, and I will want to say a disclaimer before I begin. So I won't present any new statistical methodology today. I simply was very interested in ranking data when it was first presented to me a couple of years ago. And so I thought I'd share some of my insights and some results from my work there, but only using existing statistical methodologies. All right, so what are ranking data? Well, I'm going to argue that, I'm not going to argue, you can break ranking data down as a sequence of choices. And the most basic choice is between two alternatives. So everything can come from comparisons between two things. So this is the last session of the conference. Let's start out a little bit light with some pictures of cute kittens. So in my development of these slides, I've actually named them. So on the left, we have stretching kitten, and on the right, we have peekaboo kitten. Okay, so and the question is simple. Which one do you think is cutest? So that's the most, yeah, stretching kitten. I agree. Yeah, stretching kitten is the cutest. So anyway, so there we go. That's the most basic choice, is choosing between two alternatives. And we can, of course, very quickly make that more complicated by adding more alternatives. So here we've got the same first two alternatives, stretching kitten and peekaboo kitten, and we've added laughing kitten, and I ran out of names, so plain kitten on the very right. But we're going to ask the same question again: which is the cutest? And so anyway, this time we're going to pick a laughing kitten because that's really very cute. But in doing so, I want to point out that we've actually made there's four alternatives. We've made three pairwise choices. So when we have four alternatives, we've actually said we prefer laughing kitten to stretching kitten, laughing kitten to peekaboo kitten, and laughing kitten to plain kitten. Okay, and this is a very basic part of ranking data, is that you can decompose a rank into these sequences of pairwise choices. And that's very important for a couple of other situations, or a couple of situations that I'm going to mention as we go forward. All right, so we're talking about choices. So we haven't made it to ranking data yet. We've just chosen our favorite out of a set. So what is ranking data then? Well, it's a sequence of these choices. So on the first choice we make, we have four alternatives, and we choose laughing kitten as our favorite kitten, and that's our first choice. Okay. Now, after we've removed laughing kitten from the set of alternatives, we only have three alternatives left, and we pick our favorite kitten out of the set of three alternatives, and we might choose stretching kitten in that particular case. So we rank number one, number two. So now we make a third choice, and this will be our third ranked favorite kitten. And maybe we choose peekaboo kitten. And that's the last choice we have to make. At that point, we've completely ranked the set of cutest kittens from first to fourth, because the only one left is plain kitten. And then of course this is math, so we can add numbers to these. So laughing kitten was ranked first. It was the first choice. So get the numeric label 1. Stretching kitten is second, so the numeric label 2 is assigned to stretching kitten. 3 for peekaboo kitten and 4 for plain kitten. And that is a complete ranking of the kittens that we find cutest. All right, so a bit of a caveat that doesn't come into play all of the time, but occasionally it does, and this is ordering versus ranking. So in our original sequence, we put stretching kitten, then peekaboo kitten, then laughing kitten, and plain kitten, okay? So if we were to order those images according to our ranking, we would move laughing kitten to left, and then stretching kitten, peekaboo, and plain kitten. Okay, that would be an ordering of these images reflecting our ranking. And this is kind of opposed to the numerical ranking, which I've given at the bottom and showed on the very last slide. So this is not confusing if you're talking about images and you're ordering images versus assigning these numeric ranks to images. However, if you abstract one layer further and instead of actually show images in an ordering, but you give numeric labels to each of these images, and then you order those numeric labels versus ranking those numeric labels, you can see how it gets confusing. So in the situation where you have numeric labels representing objects and you have integers, numbers representing the rankings, you have to be careful about that, the difference between those two things, because they're both permutations of small integers. Another situation that happens is partial ranks. So when you have large sets of alternatives, you may not want to rank all of them, but only say your favorite 2 or your favorite 3 or so forth. Okay, and in that case, you would have some objects, some items that are not ranked at all. You can indicate those as not ranked. Another way to think of those objects is they're tied and their ranks are lower than however many of the best top few that you're ranking are. Okay. You can also wind up in a situation with arbitrary ties where, say, the first 2 receive the same rank and the last 2 receive the same rank. Okay, so these arbitrary tie schemes also occur when it's difficult for individuals to distinguish between, say, their favorite and their second favorite. Okay. It is in those situations that decomposing ranks into sequences or collections of pairwise comparisons, that's where that becomes the most important, because any of the situations that I presented here can be decomposed and represented as those collections of pairwise comparisons. Not every collection of pairwise comparisons can be nicely represented as a ranked list. All right, so before going on, the survey that I'm going to talk about, the survey data I'm going to talk about, was part of a much larger effort by a fairly large team at NIST. I'm not expressing my preference for these 2 individuals by circling them. I'm only identifying that these were the 2 team members that I worked most closely with on this particular project. But there was a much larger team that worked on this data collection and analysis over a 5-year period. All right, so the data that I'm going to talk about today comes from a survey. And I will admit again up front, this was not a true probability survey, but instead a convenience survey. So a population of interest was identified, and they were blanketed with a survey with an attempt to get as many responses as possible. And we ended up with about 7,000 responses. But again, we do not have information about non-response rates because it was not a true probability survey. The population of interest included 911 operators, emergency medical service or emergency medical technicians, firefighters, law enforcement or police. The map here identifies the spatial distribution of the number of responses we received. The different sections and different numbers represents FEMA regions, of which there are 10 distinct FEMA regions. The highest response rates were in regions 4 and 5, so not all the way on the East Coast, but very near the East Coast. As we move west, we get fewer and fewer responses. Right. Okay. Let's see. Yeah. All right. So the survey of the first responders. Oh, I wanted to say one more thing. I'll do it at the end of this slide. Okay. So the survey of these first responders was a fairly large survey, and I'm only going to talk about a small portion of the results today, and that has to do with the ranking data. Only one of the questions was about ranking, and so on a computer, the survey respondent saw a screen like this. The tiles on the left side of the screen are communication technologies. These particular communication technologies are softwares. And on the right, you see empty spots. And the point was to just drag those tiles over. Your favorite communication software would go in the number 1 spot. Your second favorite would go in the number 2 spot, so on and so forth. Okay. And the first thing you might notice is that there's more communication technology than there are spots to drag them on the right. So what we end up with here is a partial ranking. So we do not end up with a complete ranking, only a partial ranking. For some respondents, some of the communication technologies will not be ranked. And we'll see that when we look at the data up here in some of our numerical summaries. Okay, so the one thing I wanted to point out here was that these were first responders identifying their most preferred communication technologies as used in their work. And of course, we're at a test and evaluation conference with a focus more on the military, but you could easily replace communication technologies with some other kind of technologies, and first responders could be replaced with soldiers. So the data, while not, perhaps survey responses you would necessarily see as part of this conference, that the methodology should map over to survey responses that would be of interest and more, closely related to what information the Department of Defense might be interested in. All right, so besides the ranking data, besides the responses about preferred communication technologies, of course, was also auxiliary or covariates collected. For example, one of the covariates are where you were a first responder, whether you were a first responder in a rural community or an urban suburban community. Also, what your role was within your organization, categorized into only 3 categories: P for management, supervising responder, or frontline responder. Those were determined by subject matter experts to be the most relevant categorization for roles of responders. Right. 13 minutes. Okay. So if you had attended, or if you were here for the machine learning short course that happened on Tuesday, that was the one that I attended. The Professor Adams said, the first thing he likes to do is actually look at data. And so this is one particular way to look at ranking data. So in the tables, well, it's on the axes, the horizontal axis represents different communication technologies. The vertical axis represents the rankings 1 to 5. These are only partial rankings where the maximum rank could be 5. The numbers inside of the panels are counts of each rank for each communication technology. Larger counts are made larger in text size, and the different panels delineate the different responder roles. Chiefs and managers are on the top, then supervising responders, and then, then frontline responders, and then supervising. Sorry. So very quickly from this, we can see that email is a preferred communication technology for chiefs and managers, as well as supervising responders. It has the largest count of #1 rankings. CAD, or computer aided dispatch, is the favorite communication technology of frontline responders because it has the largest count of #1 responses for frontline responders. Another thing that we could see is that language translation is one of the least popular communication technologies because it has either very few counts and the times where it was actually ranked, it was typically ranked lower 4 or 5. All right, so another way to summarize that table of information even further, ranks are numbers. They have meaning, sort of. We can just take raw averages, okay? And so here's a plot of raw averages where once again, the horizontal axis differentiates the communication technologies. The vertical axis is the average rank. And so it's ordered in such a way that lower would be more preferred. So if you have an average rank of 1, that would be the best possible average you could get. Lower is better. And we can see right away that for supervising responders and chiefs and managers, email is most preferred. For frontline responders, computer aided dispatch is most preferred. And again, language translation, of the times it was ranked, it tends to have the largest rank. So one thing that these are missing, so these are just little points, if we're going to do statistical inference, of course, we need to consider uncertainty in those estimates of average ranks. And so to do that, so we need some probability and statistics. And this was one of I was actually, when I first encountered ranking data, I was thought originally it should be multinomial, but it's not exactly multinomial, it's close. If you only give your top choice, that is multinomial distributed because you identify one out of a collection of alternatives. But when you identify your top choice and your second choice, you no longer have a multinomial distributed variable. And there are actually a couple of different models for this type of data. One of them is named the Plackette-Luce model, attributed to 2 different authors separated by about 20 years of time. There are other models, also another model named after Mallows, so maybe I believe it's the same Mallows from Mallows CP. But the Plackette-Luce model was the one that I focus on, and so I'm going to say a few words about that before we get to the results. So, no math. Last session of the conference, I took the only formula I had was on this slide, and I replaced it with a picture. So the Plackette-Luce model you can think of sort of like track racing. So you have, in a track race, you have athletes, and those athletes have some underlying strength or ability, and you run races to try to separate which athletes have the strongest ability versus the ones that have the least ability, the least strength, okay? The athletes that have the most ability will tend to win the most races or finish first or second, finish at a high position in the races. And the athletes with the least strength will tend to finish farther back. And that is the way to think about this type of model. Each alternative has some underlying strength or preference. The ones with the highest preference or the highest strength will tend to finish first or be ranked first. After a sequence of competitions, track races, or we'll get to the mapping to the surveys on the next slide, you can start to determine which of the alternatives is the strongest or most preferred and which is the weakest or least preferred. So mapping the track racing analogy to first responders, so the athletes in this case would refer to the communication, either software or devices, because they would have an underlying preference. So the communication devices have an underlying preference. And the track races in this case are the survey respondents, because each survey response provides one such ranking of the communication devices. So it gives one small piece of information about this latent strength or preference that we're trying to assess. All right, so let's move right into results here. So this graph looks a lot like the graph I showed for average rankings, except this time the vertical axis represents the estimated preference or estimated strength of the communication device, and higher in this case is better. So instead of a lower average rank, you have higher is better instead of lower is better. And also you see vertical bars associated with the points. Those are 95% credible intervals. So the analysis was done in a Bayesian way. So I'll use my terminology correctly and say these are 95% credible intervals instead of confidence intervals. So from this, we can see that indeed, email is preferred quite a lot by chiefs and managers. These are police officers. I'll look at some firefighter results in just a moment. These are police officers, and this is about software communication technologies. So chiefs and managers and supervising responders rank email very highly, and they have very similar responses for preferring email. Frontline responders prefer computer-aided dispatch in terms of software over email. And an interesting one is this one that's titled RMS, or Records Management System. So I'll highlight it here. It's right here on this side, right there on that side. So you can see that. I find that one interesting because supervising responders have some of the responsibilities of chiefs and managers and some of the responsibilities of frontline responders. And you can see with respect to that particular communication system, the supervising responders fall exactly in the middle in terms of preferences for that kind of communication technology, which seemed to make sense with the subject matter experts, because apparently records management has more to do with administrators than it does with being a frontline responder. So, all right, so here's law enforcement. So police officers again. But instead of software communication technologies, these are devices. And so right off the bat, you can see that for chiefs and managers, they prefer almost as a favorite desktop computers. That's one of their most preferred communication devices, is a desktop computer. But if you look at frontline responders, so those are the orange points and lines, you can see that they have a preference over chiefs and managers for, so MDT/MDC. So MDT is mobile data terminal. MDC stands for mobile data computer. So chiefs and managers and chiefs and managers and supervising responders prefer to have their computer on their desk, whereas frontline responders prefer to have their computer in their police car. So that comes out of the data. But more than anything, the favorite device from frontline responders is just their portable radio. And let's see, so that is, so I pointed out, portable radio is right there. Portable radio is right there. Whereas chiefs and managers, in terms of radio, they prefer the in-vehicle radio more than frontline responders and even supervising responders. Okay, a couple more results, and if there are actually, I have produced lots of graphs like this with lots of different results. If we move to firefighters and look at devices, firefighters, and switch from comparing responder roles to comparing rural versus urban suburban. Again, so we see for preferred device, urban suburban firefighters prefer a desktop computer versus smartphone actually for rural firefighters, but both of them prefer the portable radio. So whether or not you're a rural firefighter or a firefighter in an urban suburban area, portable radio is the most important communication device. If we switch to volunteer versus career, we actually see similar results to comparing rural versus urban suburban. Okay, they're very, very similar. They mimic each other closely. And so the explanation for that, according to the experts that I worked with, was that there's tons of overlap. Career firefighters tend to be in urban suburban areas. Rural firefighters tend to be volunteer firefighters. And that's why you see these very high correlation between those results. If you are, again, I've shown just a small snapshot of results here. I will point you to the report, which is freely available if you'd like to look at it, with tons of pictures like I showed on the last couple of slides, all the complete results from the survey. All right, so I'll end with a list of software only in R. I didn't actually check for software in Python. I'm sure it exists, but I didn't look for it. Software in R that can do these calculations, because these are not simple t-tests. You do need more advanced software for doing some of these calculations, like getting point estimates of latent preferences and credible intervals. I used, for this work, I used PL-Mix, which does as a Bayesian implementation of this Plackette-Luce model. And I used it primarily because it can handle partial ranks, and I just found that one package and sort of ran with it because it was the first one I found, and it was clear that it would be useful to me. Upon further searching for useful tools, I found many other packages, all of them in R with varying capabilities. All of the software that handles arbitrary ties does so by not taking in raw ranking data exactly, but taking ranking data and turning it into the set of pairwise comparisons that are implied by those ranks. And one thing I didn't mention in this is regression. So one of the packages, and only one of them I found, actually does regression. So it lets you have these underlying preferences depend explicitly on covariates, like responder role or area or some other continuous covariates, and then it will estimate coefficients associated with that. And in summary, not too bad on time. I think maybe there's time for a question if anyone has any. Thank you very much. Yes.
I was wondering how you chose to do the 5 ranking versus like having them choose their top 3 or top 7 in there.
That's a great question. And I don't have an answer for you on that. Unfortunately, I was not involved in either the design of the survey or the decisions about who to distribute it to, which is one of the reasons I wanted to say right off the bat, this was not an official probability sample. I would have fought for that, but it was not something that I was involved in. So I don't know the answer to that. So, but thank you. Very, very good question. Yeah.
Explain me what would have made it an official probability sample.
Well, so, right. So you have to go through the process of defining your population. You need to define your sampling frame. And then in some way you need to sample randomly from that sampling frame so that you can keep track of non-response and be assured that you have sampled representatively from your sampling frame and that your sampling frame matches your population at least closely enough. Yeah. So, all right. Thank you.